Good morning, everyone. Welcome to the first session of day 2 of this community meeting. Our first speaker is Pradeep Kumar Mohanty, and he'll be talking about position momenta uncertainty of classical particles in thermal bath.
Okay, welcome to this talk. And let me thank the organizers for running it for so long, like 10 years, and it's a 10th year. So thank you all organizers. So I come from IISc, Kolkata. It's a fantastic place. I also invite you to visit us at some point. So this work, uncertainty relation in classical systems, which is delta x, delta px is greater than equal to absolute angular momentum divided by 2. So this work is a part of MS thesis of Deepesh, and we have two publications, archives here. You can just very recent archives. You can look at it for details. So I will just narrate what I mean by this. So in statistical mechanics, we have ensembles, or you have systems which are isolated. So an isolated system has energy and number of particles, or matter is conserved, and we describe it by microcanonical ensemble. And then there is a closed system where energy is the only thing which exchanges with the environment. And with respect to this energy, to control energy, average energy of the system, there is external parameter, beta, which you know is temperature. So average energy of the system is a function of temperature, and number of particles or matter still remain conserved. And then there is a grand canonical ensemble where you have matter and energy. It's an open system, and energy and number of particles both fluctuate, exchange with the environment, and you have two parameters, beta and nu. Okay. So now, if you take harmonic oscillator in 2D, simple classical 2D harmonic oscillator, Hamiltonian is this, then, and the equation of motions are this, and you realize that there is no phi term here, and p phi dot equal to 0, which means that angular momentum is conserved along with energy. So there are two conserved quantities. But if you put in a thermal bath, which is at temperature T, what happens is that this parameter not only controls this, that average energy is controlled by beta, it also reset the angular momentum equal to 0. Average angular momentum is 0. Okay? So two isolated systems, let us say same energy but different L, will behave same in a thermal bath. E average equal to 0, but doesn't matter what is it earlier, so angular momentum is always 0 in a thermal bath. The question is, should we not have a canonical bath where E average equal to beta, L equal to L0 is conserved, or a grand canonical bath where E average depends on beta and mu is the one which controls the angular momentum, and both of them are fixed by some desired value. Angular momentum fluctuates but has a desired value. So this is the question, and what we get is that, well, do you have such bath? Bath basically means that you have you have a dynamical evolution, so that you start a system from somewhere, and it takes the system to equilibrium with the Boltzmann distribution at temperature T, keeping L conserved. So that is a conserved bath, and you can we devise that, and the details, the proof of the detail is very long. I'm not doing it here. So for conserved angular momentum ensemble, the equation of motion, this part up to this is, and this is the usual thing, and then just a radial damping and noise. And corresponding Fokker-Planck equation looks like this. And this one, as I said, that this will give you to the angular momentum conserved angular momentum, and you have a partition function which looks like that. So forget about the bath. This is just a simple problem to ask. You have a probability which is e to the power minus this, L square by R square plus KR square. In this, you can calculate any observable, S square average minus A average square, that I call delta A. So if you take delta X in this one, you will get this. It will depend on, K is that KR square, this harmonic term, and delta Px equal to this. So both of them, of course, depends on this. But these are increasing function of temperature. Okay, so if you take T goes to 0 and multiply these two, this will be just L by 2. Okay? Delta X, delta Px is absolute angular momentum divided by 2. So this might be true because of the, we are just talking of harmonic oscillator, but that's not right. It's true for any central potential. So for example, if you take a power law, then the equations looks like that. This is just radial damping. with a noise. And we have this, and delta x delta px is L by 2. Any k, any alpha, okay? They don't appear here. You can make a combination also, any combination of, so delta x will depend on the system parameters, delta px will depend on system parameter, the product is always half L. So maybe, no, what about other things? So now you take a non-conserved ensemble. For a non-conserved ensemble, we have a bath. I'm not telling you how we construct this bath. You can see that the damping is little complicated, like you have a gamma R square in this. So, and the noise is also a coefficient of R, but this is not a multiplicative noise, but I mean, because it goes into P phi. And this one gives you again a Boltzmann distribution with H equal to H0 minus mu P phi, okay? And then the steady state exists here when alpha less than, so alpha greater than equal to 2, the steady state exists, and for mu not equal to 0. And alpha less than 2, you have this. So alpha equal to 2 is a very special point, because that's the point below which this doesn't work, this ensemble doesn't work. And you can see that for a central potential, when alpha equal to 2, the particle motion, dynamically the particle motion looks like that. At alpha equal to 2, it has a beautiful pattern. So these are two trajectories starting from this. And there is a circle, which is the xpx, which is the limit cycle. We'll talk about this. And this is the trajectory. So now, if you go to non-central potential, the things becomes little more modified. So delta x, delta px. So v now depends on r and phi. Delta x, delta px is c times this. And the maximum value of c is half. But if you have non-central potential, you can have a 0, the trivial value, because delta x is anywhere greater than 0, delta px is greater than 0, product is anywhere greater than 0. So in some situation, you can get 0, but it cannot be bigger than half. Okay? And then there are other, also delta x, delta py, so other things which comes up, which I don't want to talk about. So for non-central potential also it works. And then if you go to more dimensions, more degrees of freedom, so then you have delta qi, delta pj is Cij times angular momentum, absolute value of average angular momentum. And this Cij defines a matrix which is non-null, always. So Cij, always, some of the uncertainties will be there. The value is always less than 1, and it's a dimensionless parameter, Cij. Okay? So what is the origin? What exactly we got here, which was missing earlier? The origin of uncertainty is here. We have if you start with Langevin equation, then you have a dissipation and a noise, and what the dissipation does, it brings the system to a potential minima with V equal to 0. And the Gaussian noise makes it fluctuate about V equal to 0. So the question is, what happens if the system doesn't bring the particle to the potential minima? There is no minima. So that is the situation where you have a limit cycle. For example, if you have a van der Pol oscillator, if you put van der Pol oscillator with a noise like this, and there is a fluctuation here, you have an uncertainty bound, but I could not calculate it exactly because this curve, the exact form of the curve is not known. But uncertainty in limit cycles, you can find it simple harmonic, 1D harmonic oscillator. I will not talk about it. You have a canonical dissipation formalism. The partition, the probability is beta h minus h0 whole square, just one. And delta x, delta px will depend on. So the statement is that wherever there is a limit cycle and there is a fluctuating motion about a limit cycle, you have a delta x, delta px, which defines the limit cycles, which depends on the shape and the period, some way. Okay? And so 2D harmonic oscillator, you can see that PR dot, this one, plus because of the conserved angular momentum, this thing comes out. And that is the one which creates a limit cycle here and creates a limit cycle in XY plane. And once it is XY plane, it's also PX, PY, and other planes. And that's the way you get the limit cycle and you get the uncertainty principle. And there is this quantum correspondence also. So I think I'll leave it here and I'll look for questions.
Any questions?
Yeah.
So, there is this notion of generalized Gibbs ensembles where you have more than one constants of motion. Or conserved quantities or nearly conserved quantities.
Yes.
So can all your discussion be extended to the generalized Gibbs ensemble?
Yes, yes, yeah.
Okay.
Yeah. So the formalism is like, if you look at these equations, they're very similar. This one. This also, like, we believe that this formally is similar to quantum mechanics. So this commutation brackets goes by a quantum bracket, and this one is the operator L. Lindblad operator here comes here. Yeah.
So
it's the same.
Yeah. So Pradeep, maybe I just missed the point. So are you saying that the limit cycle is the necessary thing to have this uncertainty ultimately?
Yeah, so that is one other statement. Doesn't matter whether it is a classical, right, whether it's a Hamiltonian system or not. Whenever there is a limit cycle, or whenever there is a jerky circular or closed curve motion, you will have some bounds. And it is also true, experimentally one can look at it in active matter systems. For example, active particles, in a harmonic trap, it makes a circular motion away from this. There also you can find out delta x, delta px will be some limit. It can be experimented, yes. We're trying that also. Any other questions?
Okay, then let's thank the speaker.
Thank you.